Swayam Prabha. Digital India. Educated India.
So, welcome back to lectures on advanced calculus for engineers, and this is here lecture number 24. We will be talking again on exact differential equations, and in particular the focus of this lecture is on integrating factor. So, how to find that function which if we multiply to an equation which is not exact and then the equation becomes exact. So, we will be looking for such functions. So, just to recall, the necessary and sufficient condition for the differential equation m dx plus n dy is equal to 0 to be exact was del m over del y is equal to del n over del x. So, what is the integrating factor? So, if an equation of this form m dx plus n dy is equal to 0 is not exact, it is sometimes possible to choose a function of x and y such that after multiplying all the terms of the equation it becomes exact, and such a multiplier is called an integrating factor. In fact, in the previous lecture we have seen in the last problem that if we multiply that equation by e power x, the equation becomes exact. But now we will discuss that how to get such an integrating factor. So, that is if I x y is an integrating factor of the given differential equation, the meaning is if we multiply this I x y to the equation. So, I x y m x y and here also I x y to this n x y term and is equal to here we have anyway 0. So, now this equation becomes an exact differential equation. Well, although an equation of the form this one has always an integrating factor or there are various integrating factors, it is not unique, but there is no general rule of finding these integrating factors. So, we will discuss some methods of finding integrating factors. So, these are some particular cases where we can easily find out the integrating factor. The number one is just by inspection. So, this is very easy sometimes, but this can be also difficult to just inspect and get that this is the function which we can multiply and then the equation will become exact. So, this method is based on the recognition of some standard exact differentials that occur frequently in practice. So, here we have to keep in mind some exact differentials which can be there in the equation just by some multiplication or manipulation we can get them in shape. So, the point here is that for instance we should know that d of x y, the differential of this x y is nothing but y dx plus x dy. This is a simple differential which we can get. Also we can get the differential of y over x which comes out to be. So, we know that the definition of the differential, we have to partially differentiate this with respect to x and then here we have dx and plus the partial derivative with respect to y of y over x and then we have dy. So, when we simplify this we will get exactly x dy minus y dx over x square. Or we have differential of x over y which is y dx minus x dy over y square. We have the differential of ln, the logarithm y over x which is x dy minus y dx over x y, and similarly for ln x over y we have these terms. The differential of tan inverse y over x is x dy minus y dx, and divided by x square plus y square. Similarly for x over y, or we have the differential of ln x y, which is y dx plus x dy over x y. So, we have to see for the given differential equation that which kind of this differential we can basically have there in the differential equation. So, here we will do some example. So, solve this differential equation y square plus 1 dx plus x y square minus 1 dy is equal to 0, for instance, and first we need to check if this is an exact differential equation. So, how to check whether this is an exact differential equation? We have to see this del m over del y is not equal to del n over del x in this particular case. So, here if we rewrite this differential equation in this form, y square, here we take common y square here also, then we have y dx and here we have x dy. So, y square when we take common, we have y dx plus x dy plus this y dx. From here again, from the first term we have y dx and from the second term we have minus x dy. So, this is what we got just by rewriting this one, which was not a exact differential equation. This is also of course not exact differential equation, it's just we have rewritten. But what is happening if we divide this by y square? If we divide this equation by y square, we have y dx plus x dy and here we have y dx minus x dy over y square. Now, both are non-differentials, both are known differentials. So, here also we know the differential and here also we know the differential. So, now this equation we can write down directly, because dxy is y dx plus x dy, which is exactly sitting here, and the differential of x over y is equal to y dx minus x dy over y square, which is also given here. So, by using those differentials, what we get, that d of x y plus d of x over y is equal to 0, and hence the solution will be x y plus this x over y is equal to this constant, or we can just multiply by y there. So, we have x y square plus x is equal to c y, that is the solution given in implicit form of the given non exact differential equation, but just by rewriting and dividing this y square makes the equation exact and we have the solution of the given differential equation. Well, a more general approach for finding out these integrating factor, the idea is to multiply the given differential equation by a function I x y and then try to choose I x y so that the resulting equation. So, this is after multiplication and we will choose now this I x y in such a way that this becomes exact, and we know the condition for the exactness. So, the above equation, this equation after multiplying by I x y is exact if and only if we have partial derivative with respect to y of I m and partial derivative of I n with respect to x. These two derivatives must be equal. Well, so if a function I satisfy this differential equation, which is basically a partial differential equation, if we can find such I, then the given equation will become exact. But the problem is that solving this above PDE, because this is a partial differential equation and finding this I out of it is like finding the solution of this differential equation, but this is very difficult and we consider only some special cases. We do not want to go into the detail of solution of PDE at this moment. So, we will make things simpler so that we have only ODEs at the end out of this PDE. So, first possibility would be that we say that an integrating factor I we are looking at, that is either a function of x alone or a function of y alone. These two possibilities we will look at out of this partial differential equation. So, in this case 1, when the above differential equation, this PDE, when I is assumed to be a function of x alone, this PDE will reduce to, because if this I is a function of x, then here it will come out. So, you have I del m over del y and equal to, here it is a function of x. So, the product rule will be applicable. So, we can do that. So, here the left hand side we will have only m I into m y, the partial derivative of m with respect to y, and the right hand side as a result of the product rule we will get I n x plus I plus n I x, or I x is equal to, so here we have the I x is equal to I m y minus I n x divided by n. So, when this is possible, when this right hand side is a function of x alone, right. So, here we have I x, and if we can divide this by I also. So, the left hand side we will have I x over I, because our assumption is that our integrating factor is a function of x alone. So, which makes sense when this right hand side m y minus this n x divided by this n, when this right hand side is a function of x alone. So, if this is a function of x alone, then you have left hand side a function of x, right hand side also a function of x. So, we have consistency, and then we can integrate this to find the I. So, if this m y minus this n x over n is a function of x only, and let us call it like f x, then by solving this differential equation d I over I is equal to f x dx, we can get I. So, here will be ln I is equal to integral f x dx, and then I will be exponential of that integral f x dx. So, by solving this we will get I as e power the integral of f x dx, our integrating factor, which is a function of x alone. Similarly, in the second case, if we assume that 1 over m and n x minus m y is a function of y alone, in that case this g y, which is we are saying here, can be used to get this integrating factor as I y is equal to e power the integral of this g y dy. So, here at least we got, after this assumption, after this simplification, two cases, that if this m y minus n x divided by n is a function of x only, we have the integrating factor, or this n x minus m y divided by m is a function of y alone, in that case also we have an integrating factor. Okay. So, here we consider this example, x square plus y square plus x and dx plus this x y dy is equal to 0. So, we check first the exactness. So, we have that condition. So, this is m, and here we have this n. So, m is equal to x square plus y square plus x, and n is x comma y. So, del m over del y is 2 times y, whereas del n over del x is simply y, del n over del x is y. So, naturally these two are not equal. So, what we do, we compute this m y minus n x. So, m y, that is 2 y minus this y over n. So, x y. So, what we realize here, that 1 over n m y minus n x is a function of x only. And if this is the case, we know that e power 1 over x dx will be the integrating factor. So, e power 1 over x dx, that is just x there, because you will have ln x there, e power ln x is x. So, this x is the integrating factor for the given differential equation. That means, if we multiply the given differential equation by x like here, then this differential equation is now exact differential equation, whose solution we can get exact either by looking at or finding out the f, or by the simple the direct trick we have. So, here using that direct formula for this exact differential equation, we can just to recall, it was m dx. So, we will integrate just this m dx term, and in the second as an integrand we will take only those terms which do not contain x. So, here anyway in this n we do not have such a term. So, that is a 0 there. So, we will just integrate this m dx, and if we integrate this, we will get here x 4 over 4. Here we will get then x square by 2 y square, and here we will get x 3 by 3, and here it is 0 anyway. Now, if we is equal to c, so if we multiply this by 12, so we will have 3 x 4, here we will have 6 x square y square, and here we will get 4 x 3 is equal to some constant. So, this will be the solution of the given differential equation, which is exactly written here: 3 x 4, 6 x square y, and 4 x 3 is equal to constant. Yeah, so that is the whole idea, that just by computing this m y minus n x and looking at whether by dividing n or by dividing m we are getting a function of x or function of y alone, and then this integrating factor will help us to convert the given differential equation into an exact differential equation whose solution can easily be found. Another example we have here: 2x y 4 e power y, and then we have 2x y 3 plus y dx. We have also this n term, which is x square y 4 e power y minus x square y square minus 3x dy is equal to 0. So, here we have m and here we have n. So, del m over del y, if we compute, it is given here, and if we compute del n over del x, it is 2x y 4 e power y minus 2x y square minus 3. So, the both are not equal. The given differential equation is not an exact differential equation. So, we see the difference del n over del x minus del m over del y, and this difference is coming minus 8 x y square e power y and minus 8 x y square minus 4, and if we take minus 4 common, we have this term. In fact, we can multiply by y and divide by y. So, here we will be having 2x y 4, 2x y cube, and then y there, which is nothing but m there. So, what we have here minus 4 by y m, that means this term here 1 over m and then n x and minus m y is equal to minus 4 over y, a function of y alone. And then we know the integrating factor, that will be e square e power integral of minus 4 over y dy. So, this is the integrating factor, e power minus 4 over y square, that means it is y power minus 4. So, if you multiply the whole equation by y power minus 4, then the given differential equation will be an exact differential equation. So, here we will have then 2x e power y, here also we have multiplied by 1 over y 4. So, we have 2x divided by y, and here 1 over y 3, and then here we have dx, plus here also we will multiply. So, we have x square e power y minus this x square over this y square, and here we will get minus 3 over this y 4 and then x, and then we have dy is equal to 0. So, this differential equation after multiplication of 1 over y 4, this will be an exact differential equation, and then we can use this direct formula to get to write the solution of the given differential equation, and which will come as x square e power y, x square over y, and x over y 3 is equal to 0, because like here in the first term we had only the 2x e power y. So, from here we will get, when we integrate this will be integrated here by with respect to x. So, we will get x square. So, this is x square y. Here we have 2x over y, when we integrate with respect to x we will have x square. So, by 2, so that x square and divided by y. In this case we have 1 over y 3 and we will integrate with respect to x. So, we will have x over y 3 and in the second term we will not have any term in n which contain only y, because all terms will contain x as well. So, that part will be 0 and then we are relating here setting this equal to a constant term. So, this is the solution of the given differential equation. Check if the following differential equation is exact. So, this is del m over del y 2y and del n over del x equal to 0, that the given differential equation is not exact. This example we have done in the previous lecture as well, where we have seen that just by multiplying e power x the equation will become exact, but now we will see that how to get that e power x for this equation. So, for that we will check this my minus nx over n in this case, and my is 2y minus this nx is also 2y. So, 2y minus this 2y, and so here we have my as 2y minus this nx is 0. So, nx is 0 and divided by the n which is again 2y. So, we will get this 1, which can be treated as a function of x alone, a function of x alone. It is a constant function basically, but we can treat it as a function of x alone and we will get this integrating factor as e power, and this function needs to be integrated with respect to x. So, 1 dx, that means e power x. So, this integrating factor what we got with this approach is e power x, which is the case earlier we have seen that if we multiply this by e power x, then this equation will become an exact differential equation. Regarding the solution of this differential equation, so we can again find this integral m dx. So, that means we have to integrate this m dx and then the term of n not containing x, but here it contains x. So, that we will not get anything, that will be the 0, integral dy 0 is equal to c. So, that will be the solution. So, here x cube by 3, then we have here x y square, then we will get here 2 x e power dx. So, that we need to integrate, and then here also we have in the second term is anyway 0, we will not get anything equal to 0. So, to integrate this we have here x square, we have here 2x and then e power x. We need to use this integration by parts, whereas in this y square e power x there will be no problem. So, we have basically the two terms in this integration. We have x square plus this 2x with e power x, where we have to partially integrate it, we have to integrate by parts, this is dx, and there is another term which is y square e power x dx, which is easy to integrate. So, what we get here x square plus 2x, the integral of e power x, and plus integral or with the minus sign, we have 2x plus 2 e power x again, and this dx plus this e power x y square. Here we have x square plus 2x e power x as it is with the minus sign again by parts. So, here we have 2x plus 2 e power x, and then minus the integral will be 2 e power x and then dx, and then we have e power x and y square. So, this is x square plus 2x together with e power x, with minus here we have minus 2x e power x, we have minus 2 e power x, and then minus minus plus we have 2 e power x plus this e power x y square. So, this 2x e power x, 2x e power x will be cancelled, and then here 2 e power x with this 2 e power x will be also cancelled. So, we have x square e power x and here e power x y square. So, basically what we got e power x and then x square plus this y square, that is the solution of this differential equation is equal to c. So, that will be the solution. So, getting the solution we will get as discussed here e power x, x square plus y square is equal to a constant. So, there are some more rules for finding integrating factors, but we are not deriving them. So, what are those? The one is that if m dx plus n dy is equal to 0 is an homogeneous expression, and then mx plus ny is not equal to 0, in that case Ixy, this 1 over mx plus ny, 1 over m into x plus 1 over n into y is an integrating factor, which directly we can use this formula. There is another one that if m dx plus n dy is equal to 0 is of this form, f1 xy into y dx, f2 xy is a function of xy, this is also a function of xy, together with this x dy is equal to 0. So, if this given differential equation is of this form, f1 xy y dx, f2 xy x dy is equal to 0, in that case this 1 over mx minus this ny is an integrating factor, provided that this mx minus ny is not equal to 0, otherwise this 1 over mx minus ny does not make any sense. So, here these there are many other rules which we are not reviewing here, but at least these two could be used. So, in this case we will just see the homogeneity of this m dx plus n dy, and then this 1 over mx plus ny will be an integrating factor, and here in this case we have to see this particular structure, and in that case this mx minus this ny will become an integrating factor of the given differential equation. So, to conclude here, we have gone through a methodology of finding the integrating factor, and what was the idea that if we multiply by Ixy to a differential equation which is not exact, but after multiplication it becomes exact. So, such a factor is called the integrating factor, and the idea of finding this integrating factor was explored here, and basically there were few rules. The important one was that if we check this my minus nx and divided by this n is a function of x only, and let us call it fx, in that case the integrating factor will be e power fx dx. So, integrating factor will become e power fx dx. Also we have seen that 1 over m nx minus my, if this is a function of y alone, then let us say that this is gy, in that case e power integral gy will be the integrating factor of that differential equation. So, here we have some references which are used for preparing this lecture, and with this I thank you very much for your attention.